Okay, so today I want to talk about problem 4 from homework 3, and I'm going to walk through it to basically give an idea of not just the correct answer to it and help people understand what they may have done wrong, but also sort of the thought process of what information needs to be included in a good answer and what does not. Some general strategies for if you miss some of these details, how to think of them in the first place. So it's going to be both reviewing this problem, but also some general problem solving advice in the context of this problem. So a reminder of the problem is consider a one-tape Turing machine, M. Um, is the language with MXN, where M on input X writes on more than n squares of its tape decidable. So we want the input to be of the form of a three-tuple. Three-tuple just means a series, like a set of ordered set of 3 items. In this case, the first one being the machine, the second one being the input to the machine, and the third one being the n squares of tape that we're writing to. So the input needs to be in that form, and we would just want to know if it satisfies this property and accept if it does and reject otherwise. So first thing I'm going to do is I want to go through a correct answer that is also succinct. Doesn't goes into the details it needs to go into, but doesn't really go into much else. Because there are some great answers, that get full credit, but they talk for like a page about something that we wouldn't expect you to write about. So this isn't just to, help you be right, but also to help students save time on, letting people know. It's really unfortunate when someone writes like a 2-page answer that's almost correct, has a page on something we didn't need details on, and then is missing like a line or two that are actually pieces of critical information that we have to take off points if we don't see, right? Because that student clearly worked very hard. They may have been able to answer the extra details if they realized those were the ones we expected. And I can understand that this feels frustrating from a student's perspective sometimes of like, well, which details do I include and which details do I not include? And that's something I want to talk about in this video. So first, let's go over a correct answer. This is not like any student's answer. This is what I wrote up just before this video. So call the language described in the problem L. Notice that unlike many problems, Janos didn't actually define a name for this language. It's really good to have like explicit definitions for things you're going to be referring to in the future, so you don't have to say like the language or this or that, because then it can become less clear. And so defining things explicitly is always good. So call the language described in the problem L. Define a configuration of M to be a 3-tuple SHT, where S is a state in M's finite state control, H is a head position, and W is what is the string on the tape. I should probably have said is the string on the tape, but regardless. It's important that I use, the reason I say finite state control, S is a state in M's finite state control, this isn't totally necessary. The textbook is quite clear that the state of a Turing machine is just like one of the elements of the finite state control. The reason I'm being so explicit here is because a lot of people, instead of talking about configurations, talked about states, right? Because in English, these are sort of almost interchangeable terms, but state, when you're talking about Turing machines, already has a definition. So one of the main reasons I'm explicitly defining what I mean by a configuration is to avoid this confusion between configurations and states. Right. So notice that if the head of M is restricted to n tape cells, the number of configurations, call this C, is finite. More specifically, if the tape alphabet has m elements, so in binary, the tape alphabet would have 0, 1, and let's say in binary, the input alphabet would have 0 and 1. The tape alphabet would have 0, 1, and blank. So let's let m be 3, just think about binary. If the tape alphabet has m elements and m has k states, m and k are finite, just in general, the number of configurations would be k times n times m to the n. Why is that? It's because there's There's k states our finite state control can be in. There's only n positions for the tape cell by assumption, which is that we've assumed that m is restricted to n tape cells. And in each of those cells, we can have one of the tape alphabet characters, right? So just like if I flip n coins and and ask how many different possibilities of series of coin flips are there, well, for each flip there's two possibilities, and I flip it n times. Here in each tape cell there's m possibilities, which is 3, and there's only n tape cells by assumption, so m to the n. So note that for any Turing machine, if a configuration ever repeats, the machine will not halt, as it will continue to return to this configuration, and there cannot be a halting condition in this loop, or the machine would have halted before repeating the configuration. This is good to point out, but the reason is, so if I repeat states in a Turing machine, that's totally fine, because if I'm in the same state, if I see a 0 or a 1, my machine might behave totally differently. But here we're assuming the configuration is identical, which means that the head is in the same position and the tape has exactly the same thing on it as it had before, and you're in the same state you were in before. So let's call some state A. If state A somehow gets back, if configuration A, once again, even I do it, but it's really important to be explicit between the states and configurations. If I'm in configuration A and I get back to configuration A, then what that means is I took a Turing machine. This machine is not random. There's no randomness. It just follows a series of instructions. And that means that in exactly the same situation, if I take steps from A, I will eventually reach the exact same configuration without halting, right? Because if I halted anywhere in between, I wouldn't have gotten from A to itself. And so where will I go now? From A again, I'll go back to A, because we already know that's how the instructions of the Turing machine are going to tell me to operate. So consider the following two-tape Turing machine that decides L. Mark the n+1th tape cell of tape 1 with an X and return the head on this tape to the leftmost position. So I'm essentially adding this X character to the tape alphabet, which is fine. And I'm also using a two-tape Turing machine, which is also fine, because what's decidable on any k-tape Turing machine is the same as for some finite k number of tapes. Is going to be decidable for any other finite k number of tapes. So 2 tapes, same as 1 tape, same as a 7 tape, no issue there. Right, so I marked the n+1th tape cell and return the head on the first tape to the leftmost position. Then I calculate C, the number of configurations, and write C on tape 2. So what I really should have said is calculate. I'm calculating this C specifically. I'm calculating a C, assuming that I'm restricted to the first n tape cells. So I actually should have been a little more explicit here, saying calculate C with the number of tape cells restricted to n, and write C on tape 2. Keeping a counter is fairly standard from class. And then the last thing I want to do is I want to simulate M, which is the input machine, on tape 1, and between each simulation step do the following. If X was read, halt and accept, right? If I read X, what that means is I'm on the n+1th tape cell. Now, in fact, a Turing machine writes at every step. This is very important. A lot of students miss this concept that a Turing machine has to write at every step. So if you are at the n+1th tape cell from the first tape cell, you must have written on tape cells 1 through n. So if you're writing on the n+1th tape cell, you've already reached the acceptance condition of this language that we're given up here. Now, the second thing is, if the counter on tape 2, so if this isn't the case, we can move on to part B of step 3. If the counter on tape 2 is 0, we halt and reject, because what this tells us is we've repeated a configuration, and we're in an infinite loop that only works on the first n tape cells, and so we can confidently reject. Otherwise, reduce the counter, because we haven't repeated the configuration yet, necessarily. We may have, but we haven't definitely done so. So otherwise, reduce the counter on tape 2. As C is finite, so this is not totally necessary in a perfect solution, but I'm trying to drive this fact home, is C is finite, the counter will reach 0 eventually, and halt the machine if no other halting condition is met, and thus L is decidable. Okay, there's a lot to unpack here. Actually, there's a lot of pitfalls, subtle and larger, and some subtle ones. And so first, what I want to go into is, let's see. I'll go into the common issues first, and then I'll go into definitions involved in this problem and ways they should be thought about. So, common issues. One is keeping track of which cells have been written in. So I do this in a relatively unique way. I think only one student solved this problem in the same way I'm doing now, which is to mark the n+1th tape cell of tape 1 with an X. Now, this isn't even what I suggested in office hours, because this is not the first thing I thought of. The first thing I thought of was more sort of brute force. And it works, and it's what most people tried, and that's fine. But if I can ever find my cursor again. Where are you? Thank you. Okay. If I mark the n+1th cell with an X, and I ever see it, then like I said, I know I've written on everything in between the first cell and the n+1th, including the n+1th now, so I can accept. This way of counting critically involves the definition of a Turing machine's transition function, forcing you to write at every step. And so if you knew that, then you could use this relatively straightforward method. If you didn't know that, then the other thing you could do is you could keep another counter. So you could keep this counter on. So this is counting number of cells. I use cells and squares interchangeably. I personally prefer the term cells. Of cells written on. Hopefully this is legible enough. I apologize for my bad computer handwriting. All right, what's the problem here? There's no explicit problem here, but there is a complication that a lot of people missed. Let's suppose that I read this and I write 0 back, and then I move over here. Oops. Oh my. So this is step 1. This is step 2. And at step 3, we're going to be back here, let's say. Let's say step 1, I write 0. So I cross this out, write 0. Again, this one, let's say I cross out and write blank. So I leave a blank there. Okay. And then back here, I see 0 again. How do I know if I've written on this tape cell before? How do I know if I've visited this tape cell before? There's no clear indication that I've written on or visited this tape cell before. So what a lot of people did is at every step, they increment this counter. So this counter would now, in binary, I guess, it depends on your alphabet, but let's just write it as 3. This counter would now read 3 in binary, let's say, because it would think that you wrote on 3 squares, but you only wrote on 2 squares. So you need a way to tell that you've written on these squares before, unless you see my way of doing it. This is actually the way I gave in office hours, which is I doubled my tape alphabet. For each tape alphabet symbol, I made a new marked version, okay, which we'll call like hat. 0 hat, 1 hat, blank hat. All right, and so when I write there the first time, instead of writing 0 there, I read the 0, I increment my counter to 1, and I write 0 hat, not 0. Second step, when I read the 1, I increment my counter to 2, and I write blank hat. Then when I move back here, I see 0 hat. So my transition function will treat 0 hat as it would treat 0, right? Because I want to simulate M on this tape, right? So I still need to act as if this is, M's transition function. But what I won't do is I won't increment the counter. Okay, so that is the way around this problem. All right, so that was the first of the most common mistakes. Another really common mistake was assuming that M is bounded to the first n tape cells. Okay, now what somebody might reasonably say is, well, I thought in your answer, Jesse, that you assumed your machine was bounded to the first n tape cells. Nope. Um, it's there's a subtle difference here. Here, I say, notice that if the head of M is restricted to n tape cells, the number of configurations is finite. So here's what I'm saying. If I assume that the head of a machine is restricted to n tape cells, then other things follow, and then I say that it follows from this that the configurations are finite. All of this relies on the assumption that M is restricted to n tape cells, though. And here, in the problem statement, we know, in fact, that it is not necessarily restricted to n tape cells. We know this because it says consider a one-tape Turing machine M. That has nothing else in it. The following Turing machine is not restricted to n tape cells. It has one state, and when it reads something, it writes this thing it just saw, and it moves right. Okay? And it just does this forever. It never halts. Then it's going to hit every tape cell. It's going to run forever, and it's going to move infinitely to the right. So there definitely exist machines that are not restricted to n tape cells, and we haven't put any restrictions on the input machine M, right? So because of that, you can't make this assumption. The reason that I write about if this assumption were true, here's the things that follow, is notice that once I write my simulating machine to decide L, I have the following line in my code, which is if X was read, halt and accept. What does that mean? Well, if I read the X, then I've worked on more than n tape cells. And if I haven't read the X, then there's no way I can't just skip. This doesn't have random access, the Turing machine, right? So because I can't just skip over this cell, I must be only in these first n tape cells. So I could only have worked on n tape cells. So the nice thing about this machine is as long as it is still running, we can assume that M has only ever written on n tape cells, because as soon as it writes on more than n tape cells, this simulating machine rejects, right? So for this line, I'm able to assume that if this line matters at all, I am in fact restricted to n tape cells. While eventually you'll want to say that we can assume n is restricted to n tape cells, M may not be. And it's only this that allows us to assume that if this machine is still running, M is restricted to n tape cells. And so that's a very important distinction. The last of the common issues before I get into sort of how to see these issues before you submit, how to correct them, how to sort of know that you don't need to write more on other topics, I'll get into immediately after this last point. So, well, leading in from the last one, I just said, you can't assume that M halts. You can't assume that M is restricted to n tape cells. You can't assume anything about it. And that aspect of M certainly led a good number of people to think this might be an undecidable problem. And I can understand where they're coming from, right? M is anything, right? And it feels like usually when we simulate M on X, that feels like a recipe for disaster to a lot of people, and that's completely reasonable. So how could and it's unfortunate because this is a mistake that is it happens so early in the answering process, and because it's not true, your answer is destined to be wrong. So if you submit that this is undecidable with a proof, your proof absolutely has some critical mistakes because it's not true. And you're unfortunately not going to have any of these sort of correct elements of you're not going to identify configurations. You're not going to identify any of the correct elements of the proof, so it's really hard to give partial credit for those answers, or very much at least, when you're being fair to other people who were at least in the right direction but made quite a few mistakes. So this is something obviously people want to avoid. Now, there's a couple ways to avoid this. First of all, while you don't know up front if it's decidable or not, obviously checking your own answers to make sure the proof is indeed logically correct is an important step of the problem solving process. And if you wrote that it was undecidable with you either some people just gave very, very weak proofs, in which case it's really hard to detect your proof is incorrect because it has almost no details. But that's its own problem. The other thing is, if you wrote a proof out, somewhere in there was a mistake. So being able to check your proof more carefully can be helpful. And if you're unsure, if you went into this problem unsure if it was decidable or undecidable, as I mentioned many people did, a really helpful technique for these types of problems is to go back and forth between the two. Try to prove it's undecidable first. Totally fine. But when you're having trouble proving it's undecidable, think about why am I having trouble proving it's undecidable? And if you're like, well, it's something about this finite n squares is a pain to work with or work around or something. It's messing up my reduction to the halting problem. That's now a hint that, well, okay, now I'll try to prove it's decidable. And since the thing that was making it hard to reduce it to the halting problem was the n squares of tape restriction, use that restriction to try and prove it's decidable. So things that are, making one proof difficult, if you're not sure it's the correct proof, can be the key to the correct proof sometimes. Another way for this specific problem that's more, just about the form of this problem is the m simulating x is certainly a hint towards this might be undecidable. We've already dealt with this sort of problem before. So the important thing is to know, well, okay, it's either going to be simulating m on x in general is questions about such things are usually not decidable. So let's look at the only additional factor here, which is this restriction to n tape cells. So we know this is going to be the deciding factor as to whether it's still undecidable or whether it's decidable now. Now the hint that it's actually going to turn the tables to make it decidable is that n is finite. Right, you're adding in a finite factor, and usually your big trouble of simulating m on x is just the inherent possible infinite things that can happen. So that when you have this new finite factor to a previously undecidable problem, it can be a strong hint that you're actually changing it to be decidable now. And if we look closely at the configurations, that is actually the key, right? Because if you look at the way we solved this problem was by talking about that if you don't leave these n tape cells, you're restricted to finite configurations. But if you think about configurations, notice that these two elements, the number of states in M and the number of symbols in our tape alphabet, are always finite. The only potentially infinite factor here is the number of tape cells we work on. So by restricting that to be finite, we've actually made this whole term finite. And that is sort of the critical observation in this problem to be certain then that it is decidable. Okay, so someone's sitting there now saying, okay, that's great. Now I know how I messed up. Still not sure how I missed it. Hopefully my explanation, at least of the thinking it's undecidable and how to find it's decidable, at least gives a better idea of how to tackle that kind of thing in the future. But I think there's still some questions up in the air for a lot of students. Like, why do I need to describe in such detail this concept of marking tape symbols is already written on, because a lot of students lost credit for saying things like, if you write on more than n plus 1 cells of tape, halt and accept. Or they even did implement a counter. They were like, use a counter for how many cells we've written in, and if it ever exceeds n, halt and accept. So why is that not okay? Especially when people are saying things like, oh, just implement a counter. See, I hear say calculate C, with n fixed based on the input and write C on tape 2. That's also not explicitly telling us how to do it. And the difference is one that comes up all the time in math and CS courses, which is that counters have been used extensively in this course. And at this point, when Janos implements a counter in class, he'll just say, okay, and then we use a counter for this. That's hinting to you, and you've already kind of gone over like how to do some basic operations on Turing machines earlier in the class. And at this point, it would just be you get too bogged down implementing counters by hand, because it's actually not as, depending on the way you want to implement the counter, you would be surprised how difficult it is to implement in Turing code, depending on the way you want to do it, or how many lines of Turing code this actually takes. As someone who's programmed a lot of Turing code, I can definitely say that how you keep your counter can vastly balloon your code. Um, However, this is something that's clearly been extracted away by the professor. It's used all the time in other questions. In fact, keeping track of which cells you've written on and which ones you haven't is actually easier than keeping a counter. Definitely going to take less lines of Turing code. Um, but it's not a problem. It's not something that's come up in class before, and it hasn't been a factor in any of the other homework questions, having to know whether I've written on a particular tape cell or not. And so because it's a new novel feature, it means it's one of the things we want to know that you're able to tackle and handle in at least a little bit of detail. Whereas we're not going to force you to write in detail counters every other problem, right? It'd be pedantic and not helpful for the learning experience. However, knowing how to do new tricks is important. Additionally, just because we don't expect you to write the counter out doesn't mean you shouldn't know how it works. And I'll get back to that a little bit later, because I know some people would have been able to figure out how to keep track if a cell had been written in or not. However, because it's a new thing we haven't seen before, if you didn't write about it, we unfortunately have to be fair to the people who did. There were a lot of people who did explicitly keep a way of telling if you'd written in a tape cell before. And as this is a new thing, we had to be fair to those students in the grading, right? And we can't just assume that someone who doesn't write about it knows it, even though I'm sure some people who wrote counters but then didn't explain how you're keeping track of where you've written before would have been able to do it if pressed. All right, so that gets to sort of this idea of, why don't I have to explain keeping a counter? But I do need to explain knowing if a tape cell has been written in before. Though if you have any further questions about it, feel free to ask me in office hours or give that as feedback to the video. To myself or Janos. So another thing that we're able to sort of abstract away is this idea of multiple tapes, right? Once again, this gets back to something we know from the textbook and from class, which is that if something's decidable in any k-tape Turing machine for a finite k, then it's decidable, right? These Turing machines are equivalent regardless of the finite number of tapes. So that does not need to be explained, even though it's sort of a non-trivial fact. Yeah, so those are some of the, why do I have to write about this? And why don't I have to write about this? And this is sort of the type of thinking that you could have about it. It's just like, has this come up in class before? If so, how much explanation does the professor give when he does stuff like this? Or has this not come up in class before? In which case I should probably give a little more detail to make sure the grader knows that I have a good understanding of these concepts. Speaking of understanding of these concepts, like I said, one of the biggest places people lost points was on obviously keeping this counter and telling if something had been written in before. And after I thought about it, after office hours, so much after office hours, when I rethought about this problem, coming up with this way of counting was much cleaner, right? It gets past that whole marking stuff issue. Sorry, I've been having some trouble with my headset. Turning off now and then. Let's make sure the sound's still working. Good. Okay, sorry about that. So, but why would you think of this? This is going to get to a very important concept that I had already pre-drawn out something for, which is that whenever you see, how would you think of this? How would you realize this? When I think a lot of people didn't really think about, does the Turing machine write at every step? Does it not write at every step? Very clearly. And I think this shows that people don't necessarily know all of the details of the definition of a Turing machine. Now, I don't actually care if people know all the... In general, I wouldn't necessarily expect someone to know all of the details of the definition of a Turing machine off the top of their head. However, when you come into a problem, one of the most important things to be able to do is read all of the component definitions and think about, do I know everything I should know about that, or should I just double check it and reread it and make sure I know the details. Because if you are missing details about definitions in a problem, it's very easy to miss corner cases and details like the ones that lost people notable amounts of points. Or to just completely misunderstand the problem and go off into left field, which is very unfortunate, right? Because then people work hard and they end up working in the totally wrong direction, and it's hard for them to get partial credit despite putting in effort. All right, so the first question I have then is, when you read this problem, how what is a Turing machine's formal definition? How many elements are there in the tuple? So I want you to think about that for a sec. Can you name all of the elements of the tuple in Turing machine, or even say how many things there are in it in Sipser's definition? Because there are many definitions of Turing machines that are equivalent. My guess is a lot of people are not going to know the answer 7, and even now that I say it's 7, I think it's 7. I hope it's 7. They probably couldn't name what each of the 7 are, and even more difficult, formally define each of those 7 elements of the tuple. So let's get to it. Okay, whew, there are 7. Good to know. So there are 7. And I checked this when grading. Like, even I would not confidently write down every piece of this definition and claim it's identical to the definition given in Sipser. So when I graded this, I need to be very pedantic about the details, and I'll get to a couple of the details that really matter in this problem. So Q is the set of states. Here's a really important thing, where it's defining what we're using states for in this class. So when you're talking about Turing machine, this is a big hint that you should not use states to mean other things. You should use some new word like configurations. And the other thing that's really, really critical in this problem is the definition of a transition function, which forces you to go from a pair of a state and a symbol to a triple of a state, a new symbol for that space, and go left or move the head left or right. Now, this means that essentially you could redefine a Turing machine so that its transition function has, in this space, the union of the tape alphabet with the operation that's just like the skip operation, where it just leaves whatever's in the tape cell the same and moves on. But because a Turing machine is defined in this way, it's essentially writing the symbol every step, even if it's the same symbol that was there before. Now, if you read this definition, you were unsure, well, does it count as writing if it's like the same as what was there before? You can always ask on Ed, because I do think that'd be a fair detail question. But you have to first think of the detailed definition of a transition function before you even think of asking such a question. But asking such a question could have made the problem notably easier. There were some people who did some really tough work that was interesting. Because you can think about Turing machines that don't have this restriction where you have to write it every step. And some people were like, well, the end cells you write on may not be contiguous. They may be completely out of order, and that vastly complicates the problems and gave some students who clearly, had some idea of this complication coming up, but didn't fully understand the definition of a Turing machine as Sipser gives it. It caused them a lot of grief, and I think wasted a lot of their time. And I know some of those students then missed other details, and maybe not because they didn't know those details, but because they spent a lot of time writing a page about, how to find the non-contiguous cells you wrote on and keep track of that. So these details, math and logic are structured like this. The definition of a TM, there's a lot of I could ask a question about just transition functions, right? And then you wouldn't ever have to talk about Turing machines. Like if I asked if you could construct transition function A from transition functions B and C. That does not involve a Turing machine, only requires this definition along with the component definitions of transition functions, which can be seen, it's everything here. So it would then involve the tape alphabet definition, it would involve Q. So below even the transition function, we have, Q and this, and we have somewhere maybe down here, we have the Cartesian product. If you don't know what this is another great example of something. If you can't formally define the Cartesian product, it's used a lot in this textbook, and it's worth knowing the formal definition. Because when we ask a problem about Turing machines, we don't expect you to go into all the components of the definition of a Turing machine, right? Just how like when we ask you a question that might involve a counter, you can just say, I'm going to use a counter. We let you say in this class, use a Turing machine to simulate this process. And that doesn't involve you stating the 7-tuple and all the component definitions. However, that's mostly for writing convenience. And because you don't need to talk about those details to be formal. However, if you don't know those details well, then it's very easy to make mistakes. So when you see that you're going to use a Turing machine, think about, well, do I know what a Turing machine is? So 7-tuple, but I don't remember all the pieces. Okay, I'll look it up. You look up the components, and you're like, okay, well, I think the transition function is really important here. Do I know exactly all these pieces of transition function? Do I know Cartesian product, exactly what that means? No. Okay, well, maybe I'll look that up. You can sometimes, there are lots of times where you can muddle through and sort of have this colloquial understanding of how these things work, but not a formal, precise definitional understanding how these works, and that can work out sometimes. But there's other times where it's going to shoot you in the foot. And the time you spend when you see a problem, just double checking the definitions and their component pieces, the time you spend on that will both A, be really well spent because you'll understand the material significantly better, and honestly, it'll improve your grades, and it might overall sort of save you time because you may write shorter answers, you may write more accurate answers and spend less time thinking about, well, what is the correct answer? I feel lost, because you may spend less time being lost if you understand the reason you may be lost is because you're forgetting some detail of the definition of something that is actually sort of the point of the question. Like the question is trying to tease out something. Like where this question is essentially trying to tease out that if you have a finite set of configurations, then you can get stuck in these loops, right? And so if you don't understand relevant definitions, then it can be very hard to see that. So I think this sort of type of thinking, I have to credit Professor Babai. He's huge on this sort of thing. This way of thinking about logic and math is very helpful. And so the Turing machine is a great example because it actually has many subtle component definitions that, if they're misunderstood, can cause trouble on this problem and many others. Right. To drive that point home, I'll give one more example of how not understanding the definition of the Turing machine fully can cause you grief. So there's a lot of other Turing machine definitions that are actually, the tape is infinite off of the left side as well as the right. Okay? If you look in CIPSR, it explicitly says that there's like a leftmost cell and other things that tell you that this is only infinite to the right. There's a picture that shows it's infinite to the right, etc., etc. However, instead of, there is yet another way to keep track of whether you've written in a cell before than making these marked characters that not many students tried, but it's a very legitimate way to go about it. I believe it was Tiago, the other TA's first idea of how he would have marked the states. So my first idea was a counter. His first idea was configuration table. And then I think the idea that I settled on after a little bit of thinking was this one. So a configuration table would just list every possible configuration, which we know is finite. And then when you see a configuration on the tape, you would cross it off from the table. And if you ever reach a configuration that's already crossed off, you know you've repeated configurations and you can halt. Now, this actually has a problem. Some students did this, and I had to double check. This was me realizing I didn't know a detail of the Turing machine definition in CIPSR, which is in many places the tape is infinite in both directions. If it was infinite in both directions, this would actually have caused a problem for this type of answer that is quite a pain to solve, honestly. The tape is infinite to the right, so this actually turns out to not be too bad. But let's consider if the input to the machine was actually, like x is length 2n. So we're going to say length of x equals 2n. Okay? So the initial input extends way out over to here. Okay? We'll say that 2nth cell is over here. And the input stops here, and then there's a bunch of blanks. Okay. Some stuff here, some symbols here. All right, so the configuration, when naively defined, takes the whole tape into account, right? But writing on n cells, if I write to the right, then I would change elements of the input. But if I write to the left, going this way, I would change some blanks, right? So these would actually lead to, so the number of possible configurations actually vastly exceeds k times n, oops, that's supposed to be n, times 3 to the n, if we're working in binary. Then the number of configurations isn't this, because the possible head positions aren't just here to here, even though I know I write at every step. Because instead of moving right, my machine could move left, right? And this would actually result in technically different configurations. It's a very fine point, and you would probably lose even if the machine definition had been such that this was a problem. I would have taken off very few points for this error because it's hard to see. But to really understand this material, like being able to notice these types of details is really important. And you will notice these types of details if you know the definition of Turing machine well and the component definitions and the components of each of these definitions well. So that's another subtlety that could have cropped up in a problem like this, where you have to really think, like, do I know exactly how this thing is defined? And like I said, looking those up, the PDF for CIPSR fortunately is free. In a textbook, this can be a little annoying because you have to go to the index and stuff. In CIPSR, I just control F Turing machine, you know, and it can be very, very quick to look up the formal definitions. So yeah, that's another subtlety that come up. All right, so I think that's enough. So basically, what I've covered is, you know, a good solution, which is here. Anybody can pause and screen grab this here early if they want to look at it more. But we also covered, so we covered an ideal answer. We covered common mistakes that I saw from a lot of students. Covered, you know, how to think about this problem a little differently so that you can avoid those mistakes, and also just sort of this hierarchical thinking about definitions, and gave this formal example of Turing machines and how they have this sort of hierarchical definitional structure where, you know, TM relies on transition function, and TM and transition function rely on states and tape alphabets, and Q does not rely on Cartesian product. But, you know, some other things can rely on, certainly this relies on Cartesian product. Depending on how you define other things, they can rely on Cartesian products. So these hierarchical definitions, and the firm example of TMs for that. All right, last thing I want to say is, please, if you don't mind just taking a minute, any feedback you'd be willing to provide with respect to this this problem review would be very helpful. You know, positive feedback. These videos take quite a bit of time to plan, record, and upload and edit if I do any of that. And so it can be really helpful to know, you know, if this is helpful. It's helpful to know because we only have so much time, and I'm happy to spend my extra time trying to help you guys with a video like this, just going over two problems in detail. But if it's not very helpful, then I won't spend my time doing that. I'll try and spend my time doing something else. So knowing that it's helpful is big. Knowing which aspects of this video were most helpful for people is huge, because then I can make sure that those are a part of any videos in the future, or that I focus on those longer, or at least, yeah. On the flip side, if this video was totally useless, that's also really useful to know. Please let me or Janosch know. Because then we will try and think of, you know, different things we can spend our time on to try and help students. Or if there were just particular parts of this video that were not helpful, that's super useful because I can leave those out. You know, if you're like, this part was super helpful, this part was not, and I wish you'd talked about this more. all three of those are things that then we can keep in mind. Okay, we'll make more of these. And we'll keep having, this element of those videos, and we'll start, you know, toning down or removing this way of talking about things. So any feedback you'd be willing to provide really helps us provide you with the best resources we can to do as well as possible in the class and learn as much from this as possible. So thanks for taking the time to watch this all the way through, and best of luck on the future homeworks and the final.